so this is the second Saturday Science of the semester. We have two more, the first week of April and the first Saturday of May. So be tuned. And today, we have pleasure to have with us Professor Kristine Delong. She's a professor at LSU in the and she works on coral skeletons, climate histories, and she will tell you about. And I was going to summarize her history, but she's going to do it herself. And I am very happy to have you here today. Today, it's Women's Day, and so it is really wonderful to see how many women there are in this room, including the speaker. So I will shut up, move to the side, and please take it away.
Yeah, thank you so much for having me. And hello, everyone. I'm Dr. Kristine Delong. And this picture I have up on the screen, this is actually from the place I'm going to talk about. This is Flower Garden Banks, and it is the closest coral reef we have to Louisiana. So did you guys know we had a coral reef here in Louisiana? No. Most people don't. It's out there, okay? So to get up to this coral reef, you have to go out on a boat. It takes about 8 hours to get out there. So you have to go on a big boat because you're going to spend the night out there. So when I did this visit to Flower Gardens, we were on the boat for 5 days. We had a really good chef on board. That was great. We did 5 dives a day. The reef is deep. So the top of the reef is at 60 feet. So to go out and dive this reef, you have to be an advanced scuba diver, which means you have to have lots of training. But when you go out there, you're going to see one of the most beautiful, healthiest reefs in U.S. waters. So I grew up in Florida, and I did all my dive training, a lot of my diving down in the Florida Keys. And the Florida Keys are one of the largest barrier reefs we have in the world. Unfortunately, it's a very sick reef. Flower Gardens is very healthy, so it's a pleasure to study that reef. So I wanted to give you a little of my background, especially to the students here who might be thinking, she does some really interesting work. Maybe I want to know, how do you get to be a paleoclimatologist? And I'm a paleoclimatologist. As I mentioned, I grew up in Florida. I did my undergrad degree in mechanical engineering. And mostly that was because in high school, I was good at math and I liked science. So my guidance counselors told me, you should be an engineer. You'll make lots of money as an engineer. So you should go to college and be an engineer. So that's what I did. But I will admittedly say, wasn't so crazy about being an engineer. I liked the training and I liked learning that sitting in a factory wasn't for me. I wanted to be out in the field and doing things and traveling. That's what I really wanted to do. So after I graduated with my mechanical engineering degree, I worked in the private sector for 10 years. I worked for various companies, mostly doing things that were new technology. So I worked in the theater industry when digital sound was just coming out, and I ran one of the first all-digital theater shows that traveled around the country. And then I worked for another company that when color digital copiers and printers were first coming out. So I did a lot of work with that new technology. I decided to go back to school and do what I wanted to do, and that was oceanography and marine science. So I went back to school in my 30s and got my master's degree and PhD at the University of South Florida. And pretty much I think the day I defended my PhD, I did my interview with LSU. So by the time I graduated, I knew I had my job at LSU, and I was getting ready to come to LSU, and I've been here for 15 years now. So that's a little of my backstory. So in the pictures I'm showing you here, the one on the left, it's me scuba diving down in the Florida Keys. The two in the middle, this is from the coast of Alabama. This is the Alabama Underwater Forest, and that's another project that I run. I actually gave a talk about the Alabama Underwater Forest 10 years ago for Saturday Science. So I'm not going to talk about that today. I'm going to talk about my coral work, but I wanted to mention I do work on other projects. So let's talk a little bit about paleoclimatology. Has anybody heard about paleoclimatology before? No? Okay. Gwendol has, but he's my PhD student. So how many of you have heard about a paleontology? So the people who study dinosaurs, right? So paleo means past. Ontology, we're talking about past life. For what paleoclimatology is, this is talking about past climates. I study climate of the past. Make sense? Now, the way we do this is a little different from what a meteorologist or a climatologist would do. So they would use instruments like thermometers and wind vanes. They use satellites to study what's happening with weather and climate today. When we talk about the past, those things didn't exist. So we have to use other tools to understand past climate. And what we use are natural archives. So things like corals and tree rings. So everybody here is familiar with trees and tree rings, right? So if you look at a cross-section of a tree, there's rings in it. You count the rings, you can tell how old the tree is, right? But guess what? Corals have rings too. The big, massive corals. And we can count those rings to tell past time. We also look at things like ice cores. They have layers in them because we have seasons. We have winters when it snows, and the summer the snow is decreased. We look at cave deposits. So those are called speleothems, and they have information in them as well. Lake records, we look at marine sediment records, all kinds of different archives can be used to tell us about the past. All right, so how do we tell or understand the past with a coral? So as I mentioned, corals have rings in them. So if you look at this x-ray here, you'll see at the very top, I've got the year 1991. So this core was collected in 1991. The coral's still alive. It's living out offshore of Veracruz, Mexico. Okay? But we know the date we took the core, and you'll see there's layers in there. And we can count those layers. The very bottom of that is 1935. So now we have a way to tell time. And if you look at my picture here in the middle, we have a coral. The coral is a lot like a jellyfish. It sits upside down, and it lives inside almost a straw. Okay? And that straw is kind of like a high-rise building. So the coral, when it's growing, it'll put down a floor, and it'll put up walls. And then it lifts itself up and puts down a new floor and new walls. So it lives on the top of its skeleton, and it builds that every single year. Now, I did put a picture here. This is a picture. This is actually Dry Tortugas down in the Florida Keys. That is a large coral colony. It's taller than me. It's hard to tell because I don't have a person there, but that's about a 6-foot-tall coral. And it lived for about 250 years. Now, the corals live in water, and because they're making their skeleton in the water that they're growing in, the chemistry of the water gets incorporated into the skeleton. Have you heard the term, you are what you eat? Okay, same thing applies to corals. So they're in the water, they're eating things in the water, they're drinking the water, the seawater, all of that goes into their skeleton. So why do we use these big, boulder, massive corals? And that's because they grow continuously, they live for many centuries. The corals that we're going to talk about today live for about 250 years. For my dissertation work, I worked on a coral from a place called New Caledonia. That coral was 10 foot tall, and it lived for over 350 years. The largest coral we have that's still alive today is about 800 years old. So they do live for a very long time. So we have these annual layers in them that help us tell time, and we're going to look at that chemistry. And we're going to use that to answer questions about what was the past ocean like where that coral was living. And we can do this with living corals. We can also do it with dead or subfossil corals. So if we go out and look at the rock record, we can find old coral reefs. We can date those using different techniques like uranium thorium dating and radiocarbon dating, and we can use those old dead corals to do reconstructions as well. All right, so this is just a map showing you all the places that I've been working on since I came to LSU. I'm going to talk about flower garden banks. So this is a location right here. So here's Louisiana. The Alabama underwater forest is there. So I'm also doing work in the Caymans, in Haiti, Dominican Republic, the Virgin Islands. We're working in Veracruz. I've worked with cave records in Belize and Florida with collaborators who've done historical document work as well with NOAA. And also done some pollen and other sediment core work with the Alabama Underwater Force. So I do lots of different things. But what I want to talk to you today about is something called the Anthropocene. And we're addressing questions that people are posing about our planet. So how many of you guys have heard the term Anthropocene? So a couple people have heard it? Okay. So how about anthropology? Everybody's heard about that, right? So anthropology is the study of humans. So what's the Anthropocene or Anthropocene? So this is a term that was posed back in the year 2000 by Paul Kristine, and he wanted to come up with a term to describe the Earth that has been modified by us, by humans. Okay? And so that's what Anthropocene means, is this is a time period of humans on our planet. And again, we're talking about changes that we've made. And this question has been posed in regards to the rock record and the geologic time scale as to, if we go back to the Jurassic, when the dinosaurs were on our planet, we can look at the rock record and we see that there's certain sets of fossils that are there, and the sediments have certain characteristics. And we know carbon dioxide was a lot higher in the atmosphere. So we know a lot about these different time periods. So Paul and others started to ask this question, can we see in the permanent rock record indications that humans have modified our planet? Is there evidence that we were here? So think about it. Let's go 100,000 years into the future or 1 million years into the future. Could a scientist go look at the rock record and see where humans first started modifying this planet? That's the question we're posing, is can we come up with a formalization to make the Anthropocene part of the geologic timescale? Now, to become part of the geologic timescale, it is an official process. There is a group that does stratigraphy that describes how we define each of these different periods of the geologic timescale. And it's a whole process, and there's rules you have to follow, and you have to do the science and bring up the evidence to do a formalization to make a particular interval part of the geologic timescale. So the way I think about this is, how many of you guys have heard of the planet Pluto? Okay? How many of you guys know it as a planet? Okay? And how many know that it's no longer a planet? Okay? So again, how did that come about? There was actually a group of scientists who made a set of rules, and then they discussed it, debated the data, and came to the understanding that Pluto is not considered a planet. So again, it's the same sort of rules that's being used here with the Anthropocene, or Anthropocene. Okay? So this is what we're working on. So the Commission on Stratigraphy put together an Anthropocene Working Group. And they were tasked with coming up with the evidence to put together a package or proposal to the Commission on Stratigraphy to officially define the Anthropocene, or Anthropocene. And they were looking at this boundary being about the mid part of the 20th century. There's lots of reasons why they picked that particular interval. One of them is during World War II and after World War II, many countries did nuclear bomb testing. Some of that testing was done in the atmosphere. And those radioactive elements and isotopes went all over the planet. And if you have people who were alive when those bomb testings went off, you probably, like my mom, sorry mom, she has these radioactive isotopes in her. So anything that was alive during this time would have recorded those events. So other things that have happened is we produce a lot of concrete. We also produce a lot of plastics. These things can also be preserved in the rock record. We've also started burning a lot of fossil fuels. And fossil fuels create pollutants. And these pollutants also can be preserved in the rock record. So we started to ask this question, can we build this evidence of, in the rock record, there are these markers. They could be chemical, they could be physical, like plastics or concrete. So is there any type of markers that are preserved that we can use to define this new part of the geologic time scale? There's a couple of chairs up here. If anybody wants to come sit. There's one here.
On there.
And there's one here. There's a couple over here. So this was the question we were tasked with doing. So the working group came up with 12 locations to go out and collect data to put together the information we needed to put this proposal together. And they selected locations that included Antarctica with ice cores. We have San Francisco Bay and Sears Lake in California. So these are going to be an estuary and a freshwater lake. We have another lake up in Canada, Crawford Lake, caves in Europe. And we also have our 2 coral sites. And I was asked to lead the Atlantic Ocean site. And my collaborator worked at Flanders Reef, which is outside the Great Barrier Reef. So that's the location for the Pacific. And we actually did work on both of those sites. So Flower Garden Banks initially was not the site we picked. We wanted to go to Little Cayman Island. And it was a place I'd recently been doing research. But then COVID happened. And you guys remember COVID, right?
Yeah,
We got stuck at home.
that thing.
And we could not travel to the Caymans. So I started thinking about what could we use that I already have to do this project. And I had this coral from Flower Garden Banks. So I talked to the Anthropocene Working Group and I said, look, I think Flower Gardens is another great site to do this because it's in the middle of nowhere. Okay? There's no people that go out there except if it's on a dive boat, right? And they have maybe about 2,000 people a year go out to visit the marine sanctuary out there. Okay? So it's far from human impacts. It's feeling what's going on in the Gulf of Mexico and the Atlantic Ocean. Because the Gulf of Mexico is the place where all the waters that are going to eventually form the Gulf Stream start. So we're going to feel all that water in the Gulf of Mexico. So I put forward Flower Gardens to be the site, and they agreed with me, and we started working on that project during COVID. So in the lab, we had one student go in and did their work, and when they were done, we shuffled in a different student, so everybody could be safe. Okay. So there's Flower Garden Banks. So just a little more on Flower Gardens. As I mentioned, it's a deep reef. Here you can see a diver coring the actual coral I'm going to show you. It's a very large coral colony called Cedastria sedaria. That's its species name. And it sits on top of the reef. The reef is a salt dome. So this is very old salt that's millions of years old that's rising up from the seafloor. And oil collects underneath that salt dome. And that's why we have so many oil wells out in the Gulf of Mexico, is because of all these salt domes. So this coral reef is surrounded by oil platforms, which is kind of neat when you go out there to dive in. So here's an x-ray from the coral. So here you can see the top was cored back in 2005. The bottom goes down to about 1930, and then we have 2 stands of that coral next to it. So again, we're using corals as our archives to tell us about the past. So here's another picture of a coral. And here you can kind of see the size of it a little better because there's a diver there. And the diver's taking the core out of the center of that colony. We also work with corals that have been uplifted. This is actually pictures from Haiti after the 2010 earthquake. So the land moved and all of these corals were pushed up out of the water. And we went out and took big pie slices out of those corals. We can also take cores out of former coral reef that is now on top of a beach. So that's my former student there, Bill. He's taking a core out of a piece of a reef that's over 125,000 years old that was washed up on the beach by a tsunami in the Cayman Islands. So we can work with really old corals to do this type of work. And that's just a picture of the cores, what they look like when we get them back on the boat, when they come back into the lab. Once they come into the lab, we slice them up like we slice bread, and then we take x-rays of them. And into those x-rays, we can count the years and tell what time it is. And here's one of my students, Medivh, working on the coral that we're actually going to talk about today. And this is actually during COVID. So he's working in the lab all by himself, taking micro samples out. And this is a little dental drill bit, and we take 12 samples out of every single annual band of the coral. Those 12 samples represent a month. Once we get that sample, we weigh it out, we're going to start to do chemistry on it. The chemistry we typically do is strontium, calcium, and oxygen isotopes. So strontium will substitute for calcium in this coral skeleton, and that substitution is based on temperature. So using a little bit of chemistry, I measure the strontium-calcium ratio in the skeleton, and I can calculate what the water temperature was when that coral was growing. And I can do that for every single month that the coral was alive. So it makes a lot of data. But we can tell a lot about the past from that data. We also measure oxygen isotopes. And I put up a little diagram here of what an isotope is, just to explain it in case you don't know. We have all the different elements. And those elements have isotopes. And what's different between each of those isotopes is the number of neutrons in the center of that atom. So for oxygen, it normally has 16, but it can have 17 or 18 as its weight. Okay? And those differences in the isotopes, chemically, if we do a reaction, it's all the same. But because there's a little heavier atom involved, it takes a little more energy for it to go through a chemical reaction. And we can use that principle to tell us things about the past. So for corals and for oxygen, that substitution of that heavier isotope into the coral skeleton is driven by temperature. But it's also driven by how much oxygen 18 is in the seawater. So if I couple my strontium calcium, which tells me temperature, and my oxygen isotopes together, I can do some calculations to determine what salinity was at that location in the past. Is everybody with me still? I know I'm starting to do some chemistry and math here. It's not scary, it's easy. Okay? You guys still with me? I see a couple of people going, it's easy. All right. Now, for the Anthropocene project, we looked at a lot of other chemistries in these corals. Probably the most that's ever been done on a single coral that I know of. So we looked at radiocarbon. You guys have heard of radiocarbon dating? Okay. So we looked at radiocarbon in the coral. We also looked at plutonium. And this is related to those atomic bomb testing and nuclear weapons testing. Okay. We also look at some other radioactive isotopes in these corals, including lead, radium, cesium, and americium. Again, all from those nuclear weapons testing. We looked at nitrogen isotopes. And nitrogen in the water tells us something about biological processes in the water. But nitrogen is also used in agriculture. So this can be a tracer of fertilizer in agriculture. We also looked at something called spheroidal carbonaceous particles, SCPs for short. Basically, these are little tiny particles that are formed when you burn coal, and they're everywhere. Or at least that's what people have told us. So we wanted to run the test to see, do we see these SCPs in corals? We also looked at microplastics. It's been in the news a lot lately. Microplastics are everywhere. Or at least that's what they're telling us, so we wanted to run the test and see if we have microplastics in corals. We also looked at carbon isotopes, which tell us about fossil fuel burning. We looked at barium calcium, which tells us about ocean processes. It can also tell us about pollution. We looked at mercury, and we also looked at the coral's growth and its health, so we can understand these changes the coral's feeling, have they had any impact on the coral, and then we also do dating. Here's a couple chairs up here if anybody wants to sit. There's a couple over here if you guys want to come over. Okay. So let's go look at the data. What did we find in our flower garden? Go ahead, you're fine. In our flower garden based coral. So this is the radiocarbon signal. And you'll notice in this data, it's kind of flat, and then it goes up high really fast. And then it kind of has been dwindling down since the 70s. This is the bomb spike from the nuclear weapons testing that was done in the Pacific Ocean. This starts in 1957, this uptick. Okay? And we looked at it in our coral from flower gardens. We also looked at another coral from flower gardens, but a different species, and also coral from Veracruz. So we're doing replication. In science, we want to make sure we've got the right results. We do things more than once. So all of these corals are seeing that same uptick about the same time. And I wanted to check all of the corals in the Atlantic Ocean. And this is a paper that we just got accepted. It's going to be published next week. So you guys are the first to see these data. Okay? So what we did here is look at all of these coral data from down in Brazil, off the coast of Venezuela, off the coast of Africa, Bermuda's included, all through the Caribbean, and in the Gulf of Mexico. And all of them have the same uptick, starting in about the year 1958, plus or minus a couple of years. So it depends on how you count your bands in your coral. But this is telling us, at least all of our corals in the Atlantic are seeing this radiocarbon bomb spike about the same time. And so again, that's one of the things we needed for the Anthropocene, is a marker that we're seeing everywhere. So we're seeing it in the corals. So next we looked at plutonium, and we looked at two different isotopes of plutonium. You'll notice it's a little different from the radiocarbon spike. So here we have increases in 1956 and 1964. These correspond directly with a particular weapons test that occurred in the Pacific. Plutonium washes out of the atmosphere very quickly, so it doesn't stick around. So that's why you see it declining. Carbon sticks around in the atmosphere. So that's why you see that increase and it's slowly declining. But this coral also has those plutonium spikes. So I wanted to look at other corals to see if they had the same thing. So we measured one of those microtolls from Haiti for plutonium, and it has the spike there in 1956. We didn't measure the year 1964, but all of our corals in the Atlantic, so those are the red dots in the map, have this spike, and also corals in the Pacific Ocean. So in the map, the red dots are the corals, the orange circles are where those nuclear weapons testing occurred. So we're seeing these plutonium spikes halfway around the world from where the weapons testing took place. And that's because the winds were moving all of that radioactivity around the planet. It went into the northern hemisphere and the southern hemisphere. All right, so now let's switch over to another isotope. This is carbon. This is the stable isotopes, not the radioactive one, that's carbon-14. This is carbon-13. And this is the coral data here from flower gardens. Again, you see it bounces around quite a bit, but we get to the year 1920, we start to see this decline in the data. And then when we get to the bottom of the record, that decline becomes very quick. So again, we want to see what could be driving this. So I plotted up here the data from the atmosphere. So this is coming from Hawaii and Antarctica, where they take air and measure those isotopes in those air samples. And you'll see it has that similar decline in the atmosphere and also that we see in the coral. So what's driving this decline? And this is fossil fuel burning. So when we drive our cars or we use coal, that oil or coal is coming from a very old source, back when the dinosaurs were alive. And at the time when these dinosaurs were alive, the carbon stable isotope value was very negative. So now when we mine those old resources, bring them back up to the surface and burn them, we're now putting all this old carbon back into the system. It's in the atmosphere, And it's going from the atmosphere and into the ocean, and the oceans are recording it as well. So this curve, where we see this decrease, this is called the Seuss effect. And we see this in corals, we see it in trees, we see it in lots of markers all around the planet. So now let's switch gears to something that's a little more of a regional signal. So this is nitrogen isotopes. So the green is the data from the coral, from out at Flower Gardens. I've plotted in blue how much nitrogen is coming down the Mississippi River. And as you'll see, it's kind of flat, and then we get to about the 1950s and 60s, and we see both the Mississippi River and the nitrogen values in the corals are changing together. And this is because the Mississippi River drains everything between the Rocky Mountains in the west to the Appalachian Mountains. So what happens in that part of our country? That's where all the agriculture is taking place, right? Lots and lots of farms, and they use fertilizers. That fertilizer has a particular nitrogen isotope signature, and that's what's driving this change that we're seeing in the corals, because it's also changing in the water out of the Gulf of Mexico. This particular marker is only in the Gulf of Mexico. We do not see it in other locations. And it's because of the Gulf of Mexico, or because of the Mississippi River. Right. And this is just some new data that we got. This is a paper we have in process. We've now extended this nitrogen record all the way back to 1755. So again, very flat in the past, very little agriculture going on. And then as we move into the present, we see that increase as we move forward. And that bright red data, that's a new core that was collected in the year 2023. And we have new data from that core as well. Okay. So then let's switch over to barium. And this is an interesting proxy that typically is connected with upwelling or river runoff. The Flower Gardens is out in the middle of the Gulf of Mexico. There's no rivers super close to it, right? And there's no upwelling out there. So this is cold water coming up from the deep. But what we do see as we move into the 1980s, this increase and a huge spike in the coral barium. If we think about oil production in the Gulf of Mexico, this spike is coinciding with the most production we had in the Gulf. And this chemical we use called barite, and that's what I've plotted here in black, is how much barite's been mined in the U.S. Barite is primarily used as a drilling mud. So when oil companies go out and drill holes into the seafloor to extract oil, they need to lubricate that hole. They use barite to do that. So they pump this mud down into the hole, it helps lubricate the core, and that barite comes out and sits on the seafloor. Okay? Now, we also have oil rigs out in the Gulf, and they produce production waters. So this is just waste that comes off the platforms, and it goes into the ocean. It also has barite in it. So what we found from looking at this coral is, one, that the variations are tracking this use of barite in the Gulf, but we also have some of the highest barium-calcium ratios in the Gulf of Mexico when we compare it to other corals that we've measured barium in all over the world. So very high barium values in the Gulf. All right, we also looked at mercury. Mercury is poisonous. I put two pictures up here. So there's some mercury in a petri dish and then a mercury thermometer. Some of y'all may have seen a mercury thermometer before. Anybody seen one? Okay. Again, if you break it, you have to get special precautions to get rid of the mercury because it evaporates easily and it will also absorb into your skin. It's dangerous. It's toxic. Okay. So in the coral, we did find these variations in mercury in the coral. So during World War II, it drops very quickly. With industrialization, it increases. As oil drilling increases in the 80s, we also have another peak. And then it declines as we have more regulations against pollution. So the very last data point you'll notice is very high. That's because that sample included the coral tissue layer. So this is the live part of the coral, has very high amounts of mercury, but the skeleton has a lot less. So not all that mercury gets incorporated into the skeleton. So we compared these mercury records against some others. So I have these blue bars. This is from a study in Bermuda. So the levels we're seeing in the Gulf of Mexico are at or higher than what we see in Bermuda waters next to a landfill. The black dots, this is from the South China Sea, and this was explained by looking at mercury pollution that's coming from industrial process in the South China Sea that was connected to their different war efforts. And then the bottom graph, I'm just plotting the mercury production in the U.S. and the world, and you'll see that we're tracking in the coral that mercury production. So last one, I'll switch now back to paleoclimate. And this is work that my PhD student Kylie's working on. You can see her happy face over there. And this is over 250 years of strontium calcium variations where we reconstructed past sea surface temperatures in the Gulf of Mexico. And if we go back in time to this period from 1750 to about 1850, 1870, this is called the Little Ice Age. And this is when in Europe things got really cold. The River Thames in London was frozen in the winter, and people could ice skate on it. Okay? So in the Gulf of Mexico, it was also colder. So it's sometimes almost 4 degrees colder than today. This is a lot colder. So as we move from that Little Ice Age period, it's been warming ever since. So as we get to today, and there you see that warming trend that everybody's heard about, global warming. So this is the temperature reconstruction. Now I want to couple some new results that we're working on. And this is bringing in those oxygen isotopes and looking at salinity. And this is really interesting. So as we go back to that Little Ice Age interval, we see that we have a mean shift from the Little Ice Age to present. So this is telling us that the Gulf of Mexico is not only getting warmer, but it's also getting saltier. And as we get to this very end of the record, we see that there's a drying trend there. So this means we're getting less evaporation coming off the Gulf of Mexico, and it's getting saltier. We're trying to explore what are the different ways this can happen. So it could mean more evaporation than precipitation. It also can mean there's changes in ocean circulation with the loop current and the Gulf Stream. It also could mean there's changes in upwelling and river runoff. But this is all new data that we're exploring in my lab right now. Okay. So you get to see a little bit of work in progress. Now, I like to compare things to other sites. This bottom is a record from Puerto Rico that was actually generated by my office mate from grad school, Holly Kilborn. And you'll see in her record, it's kind of flat, it bounces around. When you get to 1950, there's that same trend downwards, so that drying trend. And then if we go to Guadeloupe, which is in the very eastern part of the Caribbean, we also see that same trend. And this is something that meteorologists and climatologists have recognized that's happening in the Caribbean, is that there's a drying trend. They just didn't know when it started. So we're now starting to piece that story together and seeing that in the Caribbean, it looks like it started in the 1950s. In the Gulf of Mexico, it started much earlier. All right, so last one I'm going to talk about. No more chemistry. We're going to talk about coral. So this is a record of the coral's growth. And this is a project that we did with several students, including undergraduates. One of them was from a tribal college. We had undergraduates at LSU and also graduate students, counting and measuring those bands in the coral. And what we came up with is this graph that you see here. And that red line is the trend. So this coral since the 1930s has slowly been decreasing its growth. It's not growing as fast as it used to. And again, we're interested in coral health and how our changing oceans could be impacting their health. The good news is the coral's healthy, it's still alive today. And this bottom picture here, that's from flower gardens from just last summer. So it's a beautiful, healthy reef. The coral's still alive. But we can start to think about how changes in the oceans are impacting our corals. So I didn't talk about ocean acidification today, but that's another thing we worry about with corals. And I talked a lot about pollution today as well. Okay, so What were the things we didn't find with the Anthropocene? Surprise, surprise. The sporoidal SCPs were not found in the coral. So the hypothesis was that we were going to find these everywhere. We're not finding them in corals. So this was now not proposed to be one of the Anthropocene markers. We also looked for microplastics. We found no microplastics in the coral. Again, the researchers I've been working with on the microplastics, they're now starting to go to places where corals are growing right next to landfills, lots of pollution, and the more recent part of the corals are starting to have microplastics in them. But as we go back in time, we're not finding them. Okay? We also look at those other radioactive isotopes. They were not found in our coral either. So not everything worked. Some did, some didn't. That's science. That's the way it happens. So, concluding thoughts. So we put together all of our evidence, we wrote papers, and we submitted it to the Commission on Stratigraphy. Or first it went to the Anthropocene Working Group. They picked the candidate site for the Anthropocene. They picked Crawford Lake up in Canada. We were still reserved as a secondary site with flower gardens. That proposal went on to the next voting body. That voting body decided not to formalize the Anthropocene at this time. So we're not going to have a change to the geologic timescale, but we're still talking about it. We're still debating. We're thinking about how do we collect more data? How do we do more research to really formalize this? And there's lots of reasons why or why not to make it a part of the geologic timescale right now. We're still doing science. This study was an opportunity for us to learn lots of different things about corals, and we're going to continue on. So the debate and the research continues. So I just want to thank our collaborators. So Amy Wagner, she's the lady who actually collected the coral I was talking about, and my students in the lab, who they're the hard workers. They're the ones who do all the magic in the lab to produce this data. So I want to thank them as well. And oops, I'll take questions now.
So we have time for questions. So raise your hand if you have a question for Kristine.
Yes.
The drying trend, I don't understand what you mean by drying. What is it that's drying out?
So the salinities are getting higher.
Okay.
So that means that there's more salt in the ocean. And that's because either we have less precipitation, so less is evaporating out of, or more is evaporating out of the ocean, less precipitation is coming back in.
Yeah, so they're higher and it's holding moisture in it. Okay.
It can also be ocean currents have changed in the Gulf as well, so that's changing that drying trend as well. If you bring in water from the Caribbean that's saltier, then that can also change what's happening in the Gulf. Anyone else? Yes?
The mercury you talked about, you found the coral, was it organic or inorganic mercury?
Inorganic. Yeah, it's in the coral skeleton. Yeah, that tissue layer would be organic. So, other questions?
Was there any evidence of bleached coral? Was there any differences in the layers?
Good question. In these corals, no, and that's because Flower Gardens is a really healthy reef. They haven't experienced a lot of bleaching out there. They did have a disease outbreak back in 2021. So yes, there's disease outbreaks. It doesn't always show up in the skeleton. And because this is a deeper reef, they tend not to bleach out there. Versus going like to the Florida Keys, the reefs there are very shallow. So going from like almost the surface down to 20, 30 feet, yes, there's extensive bleaching happening there. So we went to Curacao to do some coring. That was 23, and that was in February of 23. The corals bleached there in the summer, and when we went back in 24 to do more coring in February, a lot of the corals were dead. unfortunately. Other questions?
You said there's a lot of reasons to like support and deny the existence of the Anthropocene.
Mm-hmm.
I'm just curious, like, what is your kind of expert opinion after you were actually doing the research?
Right. You do see markers that are showing up in lots of places. So like the radiocarbon and the isotopes. So some of the criticism of the radioactive isotopes is things like radiocarbon. When you get to about 48,000 years ago, there's no radiocarbon left, it's all decayed. So if you were to go into the future, 50,000 years, and try to measure the radiocarbon in those corals, it would be 0. So it's not a permanent marker. So again, that's some of the criticism of our proposal was in the future, 50,000 years, our marker would be there. So yeah, so it comes down to definitions. So, yeah, I'll leave it there. Other questions?
I asked you before, of interest for the rest. When you take the data, you and your group, what is your relation with sharks?
Yes, so I love the scuba dive. It's awesome. Yes, I see sharks. I've been in water with sharks. It's actually kind of cool to see a shark in the water. There's a lot of negative thoughts about sharks. People are going out and killing them. They also will harvest them for shark fin soup. So particularly in the Pacific Ocean. First few times I went to Hawaii, we saw lots of sharks. Last time I went to Hawaii, it was 2017, we didn't see a shark the whole week. So it's almost a privilege now to see a shark in the water. So down in the Keys, maybe I'll see a couple nurse sharks sleeping underneath the corals. Never see any big oceanic sharks in the Keys. Curacao, we were there for 5 days, never saw a shark. Did see a stingray. So stingray was very interested in what we were doing with the coral. So every time we pulled the core string out, the stingray would come sit on top of the hole, just sitting there eating up all the little dredgings that we brought up. So yeah, so I'm not scared of sharks. But again, places I go, there's no great whites. I will say that too. I don't want to go in the water for great whites. And I'm not crazy about tiger sharks either. I have been in the water with a bull shark. In Florida, there's lots of bull sharks. But again, the bubbles that divers make, sharks don't like it, so they tend to run away. If you're going out diving in the Keys and you want to see a shark, you're the first person in the water. Because once everybody else in the boat gets in the water, the sharks are scared and they just kind of the key there if you want to see a shark. Be the first in the water. Make lots of bubbles.
More questions?
So, anybody want to be a marine scientist in the future? Or be a scientist in the future? Any kind of scientist? Did I scare you guys? No, this is fun stuff. You get to go all over the place, yes.
So if they had added the Anthropocene to the geologic record, what are the consequences of that? Is it just that it gets put in textbooks, or there's some like repercussions?
Right, it goes into textbooks, it becomes a formal part of the geologic timescale. I think it's more of the recognition that we've changed our climate, and it's a permanent change.
Yeah.
So it's kind of making that statement of we've permanently changed the climate. And it's now embedded in the climate. But yeah, I think otherwise, I don't think there's other repercussions. It's mostly for science.
What about oil spills in the Gulf of Mexico? Are they recorded?
Good question. We had the BT oil spill happen. I did not work on it, but I had collaborators, people I know who did work on corals and looking at oil in the corals. Some of the deep sea corals, they did find indications of oil pollution from that event. Flower Gardens did not get any of the deep sea corals. So it was far enough away, all the oil still would be from the direction. So they were safe, but some of those deep sea corals, so these are corals growing down at like 2,000, 4,000 feet. They're little tiny corals, they grow like big branches. Yes, they did on communication.
Any more questions?
Yes.
Does the leveling of the river have any implications for the salinity that on the Gulf of Mexico?
Good question. So putting up levees?
Yeah.
So water that normally would have overflowed and go out over the land. So all of that sediment, anything in that sediment, it's now all being pushed out to the Gulf. So levees are probably part of the reason we see that trend in the nitrogen, because we no longer have those regular flooding events. It's kind of like a superhighway of all of that water going out to the Gulf. So yeah, that's part of it too. Other questions? Yes.
In related to the last question, when you say that the efforts towards the Louisiana like marshes and wetlands would have a similar effect, like the levees, you think, on nitrogen and sediments?
Oh yeah. Yeah, they're all changing. I have colleagues at LSU, those are questions that they work on, is understanding the nitrogen carbon cycles and how those are changing out in the estuaries, our mangrove forests, and our saltwater grasses, and then also how river diversions could change that. So yeah, they're all important questions. And there's folks at LSU who are working on those questions. Yes.
As far as the salinity is concerned, you said that it was an increase in salinity due to evaporation and
Or less precipitation.
or less
combination
precipitation. Combination of both. The ocean currents are highly impacting climate change or shift or whatever you want to call it. How does the salinity impact the ocean currents?
Right. Good question. So again, it depends on the type of currents you're talking about. At the surface, most of those currents are being driven by the wind. So the wind blows along the surface and moves the water. As you go down deeper into the water, those currents are being driven by density. And density is connected to salinity. So as you change the salinity of the Gulf, you're going to change those deeper water currents as well. So yeah, it's a question I've been kind of kicking around for the last 10 years. This little ice age, we're getting a lot of cooling. It's like cooling like the end of the ice age in the Gulf. So again, how do you cool the Gulf that much? One of my hypotheses is that the current was kind of coming up through between Yucatan and Cuba, and just staying right along Cuba, and then exiting out into the Florida current and into the Gulf Stream. So it wasn't doing the big loop into the Gulf. So all that heat from the Caribbean wasn't coming into the Gulf. So again, that's something I'm working with climate modelers on to try to understand how do we cool the Gulf that much. And it could be linked back to the salinity chain as well. So yeah, so there are questions we're still working on.
That right now it's cooling, or
Right now, it's getting hotter and salter. So if we go back 250 years, it was cooler and less salt.
All the data that you use, I imagine, was not taken by your group. Data in other places around the world.
Right.
How do you share the data?
Right.
What is the policy for?
Right. So yes, we share the data. I work closely with Flower Garden Bay's National Marine Sanctuary. So they've seen all the data. They were part of the process. We work with labs all around the world. The mercury is done in London. The spheroidal carbonaceous particles was also done in Manchester in the UK. The nitrogen isotopes that was done in Germany. So yeah, my lab didn't do everything. We sent it to labs all over the place. We had a group of about 50 scientists working on the Anthropocene project.
So there is a long list of authors.
Yes.
Of those articles.
Yes, very long list. So
It's a collaboration.
some of them we did in our lab, and my students did it, but the others, especially like the plutonium and the other radioactive isotopes, those were the very specialized labs that just measure those isotopes. For the plutonium, our samples sat in the counter for 3 months.
before they could get enough counts on it. So it took a very long time to get that plutonium. So, and they did the plutonium for the other coral site as well. So yeah, it was quite an undertaking to pull it all together. Yes?
Do you have an estimate how much this project costs?
Good idea. We received a grant from the Museum of World Cultures in Berlin to help cover some of our analysis. That was $48,000. Most of this was donated time and donated resources. So like at the beginning of my slide, I mentioned National Science Foundation. I have other grants with them. So the strontium, calcium, and oxygen isotopes, that was all paid for off the National Science Foundation grant. I'm also part of the South Central Climate Adaptation Science Center, so they paid for part of it. There's other labs around the world that did these analysis, they did it for free, or they had other funding sources. If I had to put together a budget to do this research and pay for it all, probably in the neighborhood of $2 to $3 million. So, for the analysis and then pay for the work. This is big science. It's expensive. But as scientists, we're really good at stretching a dollar. Ask my grad students. I could stretch a dollar pretty good. Other questions?
Okay. Jamie, thank you.
April 5th, Saturday, and that will also be on climate issues, carbon dioxide, and you have heard of projects to put carbon dioxide into the ground. In fact, there's a big project starting at LSU to drill 8,000 feet below campus. So you can hear about that April 5th.
Will be in the main room. Will not be in April. The next talk will not be in this room, but in the main room.